Alright, so I want to start this by talking about, I'm talking about general relativity in this playlist, and I want to start off just by giving a broad overview. Now, general relativity is extremely complex, and the way by which we go about sort of organizing our ideas, or the way I go about sort of organizing my ideas when it comes to studying general relativity, is in terms of this guy right here, G mu nu. Now you might think, what in the world is this? Okay, for those of you who have been exposed to GR, you obviously know what this is. This is the metric tensor. This is the metric tensor. Right, but I do want to give some background. I do want to give some background to this, and so I'm going to start off by considering the Pythagorean Theorem. This to me is the most intuitive way to understand this metric tensor. Okay, and then I'm going to go back and we're gonna look at this guy in depth. We're going to look at the various forms that it can take on in GR and advanced GR. So again, I want to start off with the Pythagorean Theorem, where we have some triangle, and we want to know what the distance. We'll call this side ds, and we'll call this dx1, and this side dx2. Right? This might be synonymous with like the y coordinate if you're on an xy plane, but to be general and to allow ourselves multiple dimensions, I'm going to call this just this, the length of this is dx1 and the length of this is dx2. And again, we have, this is a 90-degree angle. Right? And we want to know what the distance is of this ds right here. So we know from Pythagoras that ds squared equals dx1 squared plus dx2 squared. Right? This is kind of like the same thing as a squared plus b squared equals c squared. We're just naming them differently. Right, so I'm actually going to write this out in a little bit more detail. So I have dx1 squared is the same thing as dx1 times dx1 plus dx2 dx2. And we can do this infinitely if we had a three-dimensional system, we would just do dx3, dx3, dx4, dx4, and so on. But right now we're just dealing in 2 dimensions, right, where this sort of subscript here gives us the dimensionality of our space that we're in. Right, so right now we're just doing this on 2 dimensions, on a 2-dimensional plane. And here we have our distance. Right, so this is the square of our distance, right? So if we wanted to know the distance, then we would take the square root of this. But before I do that, I am going to say that this is equal to the sum, this right here, if you haven't seen this before, this is called the sum of dxi dxj. Right, and we're summing over I and j for as many dimensions as we want. So in this case, this is just 2. So if I were to just do in 2 dimensions, I would go like that. But we need to add something right here. We need to add this thing right here. Now this guy right here, this is called the Kronecker Delta. Kronecker Delta. This is a GR course, not a spelling course. But the Kronecker Delta tells us the Kronecker Delta here is equal. Delta ij is equal to 2 values. It's equal to 0 and 1. It's equal to 0 when or if I is not equal to j, and 1 if I is equal to j. All right, so far so good. So if we were to sort of write this out, we would have dx1 dx1 Kronecker 1 right, and then dx1 dx2 Kronecker Delta 1 2 dx and then we have dx2 dx1 Kronecker Delta 2 1 and dx 2 dx2 Kronecker Delta 2 2. Now again, here we said that it's 0 if I does not equal j. Here these two are not equal, so we can ultimately say by to this one and by to this one. Okay. I'm going to move that over just a little bit. My apologies for background music. My dog is playing around with her toys. And so again, we just get this term right here and this term right here. But again, Kronecker Delta is just 1, and we recover dx1 plus dx2 dx2. So this right here, so I'll write it again. So our distance, it's always good to remind ourselves what this actually equals. This is equals our distance, dx I dxj Kronecker Delta I j. And then we're summing over I, and we're summing over j, and we're going to d dimensions. In our case, we're just going to do 2. So I'm just putting a 2 right here. Now, I realize this is it's a sort of a mathy introduction, but this is an introduction nevertheless to really get at what this metric tensor is going to be. So now that we have sort of this definition for the distance ds, we could say now, we can actually generalize this principle. This here, this right here, in flat space, right? We're on a flat plane here. This is on a flat plane, where if we're doing Pythagorean Theorem, here's our ds value. If we're doing our Pythagorean Theorem on flat space, this guy right here works, right? In physics, this is sort of translated to dxi dxj, and then we have this eta ij. Again, we're summing over I, and we're summing over j, and we're going to 2. This right here is the Minkowski metric. So the Minkowski metric. All right, and I might go into the history of who these people are. Minkowski he knew Einstein very well, and he worked. A lot of his work was in GR. All right, but more generally, this only works for flat space, where these values take on 1. Again, the Minkowski metric is just like, it's almost equivalent to the Kronecker Delta, right? But we understand the Minkowski metric more as a matrix that looks something like this: -1, 1, 1, 1, and everything in here is 0. All right, and everything, so everything here is 0. So when we do this, when we actually do this multiplication out with this matrix, we recover this again, and we can do that. But this is a very specific case. This is a specific case for flat space. So this is ds in flat space. Right. So if we have dxi, dxj, if we have now, we change this to a gij, a more general form, this doesn't necessarily have to be all ones down the diagonal, right? This could be different values along the diagonal. And again, we're operating in two-dimensional space here. Again, we don't have to operate in two-dimensional space, but this right here is our metric tensor. Denser. Tensor, metric. So why do we call this a tensor? I'm actually going to go through this a little bit more in depth later on, but we call this a tensor because this object right here, we call this a mathematical object. So gij is a mathematical object such that when it's applied to two vectors, again, these two guys are vectors. Two little infinitesimal vectors. Remember, so this is ds squared. When we were doing something like this, we're kind of doing this vector summation almost, where these guys are, here's our dx1, and here's our dx2. Right, so these guys they're vectors, right? gij takes these two vectors, right? And what does it produce? Well, ds squared is not a vector. This is a number, and it's a number, it's a scalar, such that, or this is a scalar that represents the magnitude, the square of the magnitude of this distance right here. Okay? So gij takes in two vectors, and produces a scalar. And this is how we're going to want to think about this. A tensor of rank, this happens to be a tensor of rank 2. So a tensor of rank 2 tensor, so a rank 2 tensor takes two vectors and it outputs a scalar. Okay. So two vectors go into a rank 2 tensor, and we get a scalar out of that. And the scalar represents the magnitude of some distance. Of a distance. Okay. So I'm going to just rewrite this again. So ds squared is equal to the sum of dxi, dxj, gij. We don't really know what the form of this gij is yet. Again, this could be a matrix with anything down the diagonal. We're summing over I and j, and we're going across the dimensions d. I'll make this more general now. Well, so how do we actually want to acquire the actual distance? Right, so this is a distance squared. Well, we take the square root. Okay, so if we take the square root of ds, we just get, or ds squared, we just get ds. All right, sorry about that noise. That's my dog having fun with her toys. This is equal to now the square root of all of this. So if I just take the... okay, my dog is bumping the table. Give me 1 second here, I'll redo that. Okay, this is the square root of all of this stuff in here. dxj g I j. Okay. All right. Well, this actually is pretty interesting. So it tells us now that the ds, we could split this apart. We could say the square root of g I j, right, times the square root of all the rest in here. So again, dxi dxj ij d, like that. All right, so we have this. So this here is our distance, right? But this here, now we have the square root of g. We have this interesting sort of square root of gij here. Well, we can't really take the square root of a matrix. What's going to be interesting to us later on, right, is the square root of the determinant. And when we say the determinant in general relativity, especially the determinant of this guy right here, the determinant of this matrix, or this tensor, the square root of it, now we can take the square root of it by doing this right here. Okay, and we'll test this. We'll see what happens if we take a specific form of this metric. Again, this metric can take on different forms. It can take on the most common case that we'll study is the Schwarzschild form, Schwart, Schwarzschild, I think is how you spell it. Metric. We can have the Schwarzschild metric. We can have the Kerr metric. The Kerr metric again, so this tells us something about black holes. This will tell us something about the black hole, the physics of black holes and what happens around a black hole. The Kerr metric will tell us something about rotating black holes. Rotating black holes. Okay, my dog is being super annoying. We can have the Ernst metric. This is rotating, I believe it's rotating, if I remember correctly, rotating magnetically charged black holes. Right? So this metric can take on various different forms in various different areas of space. Right? So imagine we're in some space here, right? And we have some black hole. Here's some black hole. And so this metric right here, perhaps at this point, is going to tell us something about the notion of distance, again, because this tells us something about the notion of distance, right? When we are near this black hole, and depending on the properties of this black hole again, the properties of this black hole will tell us ultimately something about G, what G looks like, right? So we go from understanding now what G is, and throughout this playlist, we're going to take a look at the various forms that it can take on, and derive some of the various forms that it can take on. But nevertheless, G is our most important It's our most important object, mathematical object, that we're interested in studying when it comes to studying GR. Because from G, we'll be able to calculate these things called Christoffel symbols. Right, so metric tensor. Then we'll be able to calculate these things called Christoffel symbols. And then from there, we'll be able to calculate these things called the most important object here. And I'll just say ij, and then ij. This might not be totally correct here, but this is the Riemann, the placement of this ij here. It might not necessarily be the same as this ij here. Well, we'll go more into the derivation here. I'm just sort of giving a canonical outline here. The Riemann curvature tensor. You can see here that this is a rank 4 tensor. So we go from a rank 2 tensor to a rank 4 tensor. And then from the Riemann curvature tensor, we'll be able to calculate this thing called the Richie tensor. Right? The Richie tensor is another 2 rank tensor. So the Richie tensor. And so the Richie tensor, so we have all these objects, these mathematical objects that are going to be of interest to us. We'll also be able to define other types of objects like intrinsic and extrinsic curvature that are presented in papers. So Kij, I believe, is something that is presented in a paper that I read as the extrinsic curvature tensor. And then we can also have another one, I think they denote it as Jij. I might be off with the namings of these, but then we have intrinsic curvature and so forth. With these objects in mind, though, we can do a lot. We can be able to then define other objects, other types of objects. There's these objects called, I can't remember what the name of them are, but they're denoted as FAB. And they actually come from the metric. So not the Christoffel symbols, but they come from the metric. And these guys, FAB and NABC, these are interesting thermodynamic. They'll tell us something about the thermodynamics. Right. The Richie curvature tensor, the Richie tensor again, will tell us in conjunction with the metric tensor. So R and G will tell us something about. Oh, my pen is going weird. Will tell us something about the dynamics. That will give us something called the Lagrangian, and it'll be in terms of R. Oh, my pen is freaking out. And G. All right, so I fixed this a little bit. So L here is the Lagrangian, and this L, this curvy L right here is the Lagrangian, and we see that once we know G and once we know R, then it's a straight shot to the Lagrangian, right? And if you don't know what the Lagrangian is yet, we'll cover that in later lectures. But this is to say that the metric tensor is really connected to almost anything you could possibly think of when it comes to assessing the physics and studying the physics of spacetime. right? And then from the Lagrangian, we can get the action, which is S. Right, and so I took the pleasure of putting a little bit of a summary here so far. So this G mu nu defines a sense of distance. Right? From the sense of distance, we can get these items, these mathematical objects, this Riemann curvature tensor and a Richie curvature tensor. We can get these objects from this metric tensor. Right? So from a distance, we can get curvature. And curvature is ultimately what is interesting to us. We want to know exactly. We want to know what the curvature of space is. I remember I read somewhere that the second derivative of anything is what makes life possible. It's possible to have constant positions, constant distances, but when you're traveling, the curvature plays a big role in dictating dictating life, dictating the dynamics by which things happen. So this summary isn't totally complete because in the previous slide I showed that we have that this R mu nu here, this Richie curvature tensor, also shows up in the Lagrangian, and the dynamics is right here. But we see right here that there's a connection between dynamics and curvature. Right? These guys are ultimately related to this guy, which is ultimately shows up in this guy. And these guys here, this is the Hamiltonian. The Hamiltonian and Lagrangian are transforms of one another. And then we can also look at the thermodynamics. This is a little bit of a question area. I don't know at what point I'm going to get to these, but I'm going to be going over a paper that covers the thermodynamics of space-time as well. These guys here are intrinsic and extrinsic curvature tensors, and we're going to look at all of this. And so here's my black hole or whatever I'm looking at in the universe. And it's embedded in some space-time, some curvature here. Make that arrow look a little nicer. And this is what tells us G, right? We're interested in G to the extent that it satisfies the dynamics that we observe in the universe. And those dynamics are governed by this big guy right here, the Einstein field equation. This is not one equation, this is actually many equations in which G mu nu actually shows up. This is the metric tensor, shows up in Einstein's field equations. Here's the Richie curvature tensor. And here is something called, this is the tensor that relates, that's escaping my mind right now, but it relates the mass and the mass of the object. And what this equation is telling us is that curvature, so we have all these curvature items on one side of the equation. It tells us something about the mass that is embedded within our field. All right, so this is mass tensor. Right, it has a different name. It's just escaping my mind right now. But this is all connected. We have some space-time that has some dynamics that obeys the Einstein field equations, right? And so we need to find G mu nu that satisfies the field equations. And when we find G mu nu, we can then calculate all these interesting guys right here. Okay, so now that we have this sort of established, there's a few more things I want to go over before I go into the next topic here. And one of those things is the difference between covariant and contravariant objects. This video is going to be kind of long because I want to get a lot of the preliminary stuff out of the way so we can start doing a lot of interesting stuff later. So when we're talking about covariant and contravariant objects, covariant and contravariant objects, we are interested in how things transform under different systems of measurement. And so I'm going to do this with an example. So consider force. The force of a particle equals the mass of the particle times the acceleration, right? And over here, I'm going to pull out the equation for the electric field, which is given by the charge of some object divided by the distance that you are away from that charged object, right? And F again is a vector. E is a vector. The electric field is a vector at every point in space. The force is a vector as well. And so what can we? Well, what is there some sort of fundamental difference between this vector right here and this vector, other than the fact that one is a force and the other is a field? Well, we can say that if A, in this case, so if the acceleration is 9.8 meters per second squared, and we translate that to, and then we use a different coordinate system, and say that this is 0.0098 meters per, or not meters. This is the same thing as kilometers per second squared. Right? The component, this here is the component, decrease. So the value of the force decreases as we increased the means by which we measure. We went from meters to kilometers, right? So that increased because kilometers are bigger than meters. But this right here decreased. So the component, the value of the force decreased as we increased our basis. And so F is we could say that F is a contravariant object or vector / vector. And so that's to say that it translates contravariantly or oppositely than how the basis is translated. The basis is translated from meters to kilometers, whereas the components of the vector of the force vector decrease, right, from 9.8 to 0.0098. If in the case of the electric field, say we measure the distance between our charge to be 10 meters, and we transform our basis to kilometers, what happens to the electric field, right? So 10 kilometers, it goes to, this is 0.01 kilometers, right? So it's, as we decrease the denominator here, the value of E actually increases. So in that case, E, the electric field, covariantly transforms. So this is so now we have these two different fundamental objects. One is a contravariant vector, and the other is a covariant vector, right? And this all has to do with transformations. Between bases. transformations between bases, and this is a key concept here. This is a very key concept because we want it ultimately comes down to how things transform. How things transform in terms of a lot of this. How things transform is gonna play a big role in general relativity, and it's gonna play a big role in many other disciplines as well, right? And so just a couple of nomenclature, sort of a little bit of nomenclature here. We have f vector, we called the f vector a contravariant object. This is usually denoted, if f is a vector, as we put the indices of our vector on the top here, on the top left, or on the top right part of the vector. Here, the E vector is denoted, or if it's covariant, below, that's sort of how I remember it. Its components are listed below here. And we can understand this by looking at this in terms of a vector. If we looked at this in terms of a regular vector, this is sort of translated into F1, F2, actually I'll put F0 here as well, F3, where each one of these components refers to the orthonormal direction, or the orthogonal direction, in some plane. So this is the component of f along the x-axis. This F2 is a component of f along the y-axis, and F3 is a component of y along the z-axis. And in general relativity, we're often also interested in the time axis, right? Similarly here, E bottom mu can be translated as the component of the electric field in the time dimension, the component of the electric field in the x direction, component of the electric field in the y direction, and component of the electric field in the z direction, right? And these are usually almost always placed with numbers, just like I did here. So this would actually be E0, E1, E2, and E3. And here we're operating in 4 dimensions, right? So this is a 4-dimensional space, or space-time, if you will, because again, this is the time component of this vector, and all these are all the spatial components. So spatial components, and this is the time component, or temporal component. So this is going to be really important. There's a couple of other ways we'll be able to denote this kind of stuff that you will see very frequently in general relativity and even in quantum mechanics, because the idea here is that every covariant object, every contravariant object, every covariant contravariant object, f mu will result in the magnitude of the force. And you can sort of intuitively now begin to understand why this might be the case, because again, the magnitude is a combination. It's something squared. Remember when we talked about so the ds squared is equal to the square of dx1 squared plus dx2 squared, right? So we need the contravariant vector and the covariant vector to get the scalar that truly represents the magnitude of our vector. Right? And f mu, so this little mu part here, again, these sum over, this is equivalent, all of this is equivalent to f0 plus f1 plus f2, and so on, right? These are this is how we construct the magnitude of the vector squared, depending on how you look at this, because again the ds was squared in that case when we did Pythagorean Theorem. And so this is very important to know. We need the counterpart. We need the covariant and the contravariant part of whatever vector we're looking at if we're interested in getting some fundamental scalar associated with the magnitude of the vector. And of course this can go on into infinite dimensional spaces, right? We don't necessarily have to stop at 3. We don't necessarily have to stop at 4 either. We could keep going on to get some interesting notions of the magnitude of this force. And so a little bit more notation. We have F1, the basis on F1. Actually, I will start with F0 just to be a little bit more consistent. Sorry about the dog making noise. So we have F0 dx 0. Actually, this 0 should be down here because this is a covariant object with a contravariant object, and this is going to give us some value that we can. So here dx1 f2 dx2 f3 dx3. So these are the basis. This is the basis part. So the basis applied to the component will give us ultimately the vector that we want. And so we can write this in full generality. If we want to know what f is, it's equal to f0 dx0 plus f1 dx1 plus f2 dx2, and so on. And we can do the same thing with contravariant or with covariant objects. This would be E0 dx0 plus E1 dx1. Right, we just need here, because we had, this is a scalar, the magnitude of this guy is a scalar, so we need to add scalars together. So this is a scalar, this is a scalar, this is a scalar. So if we want to get a scalar out of one of these objects, we need to apply it to some covariant object as well. So the basis on this f are covariant, and the basis on this e are contravariant. But again, there's nothing stopping us. If we went e mu like this, there's nothing stopping us from doing E0 dx0 and so on. Right? This is just the contravariant component of E, such that when we do this, we get E, like that. Right, so again, this is just an intro to some of the ideas that need to get covered. And so I'll go into this a lot deeper. But what I'll say lastly is we came across this idea of Gij as the metric tensor. Right, so the metric tensor, again, these are two covariant, or this is a covariant object. This is rank 2 covariant object. But there's nothing stopping us from having something like this, right? And the relationship between the two, what is the relationship between the two? Well, the relationship between the two is that if we were to treat these as matrices, one is the inverse of the other, such that I get Ij, Gij. This is a little bit of informal notation. This is usually supposed to be mu nu, G mu nu. That should equal our unit vector. So one is the inverse of the other, or our unit matrix. And the determinant of the unit matrix, the determinant, so the determinant of this G mu nu, G mu nu, is the dimensionality of our space. It's usually denoted n, but maybe for not confusing you, this is the dimensionality. I'm spelling that wrong. I'll just call it D. So this is dimensions. This is the dimensionality of our space. So we have now, so G mu nu, again, coming back to this picture here, this gives us the notion of distance and dimensionality. This is a very important object. It's distance and dimensionality, right? And it exists everywhere in space. So if I have some space, I have right here a G mu nu. Right here, I have a G mu nu. And there's nothing, these two objects here, there's nothing stopping us from saying that one might be different than the other, right? Because you might have a black hole right here. I have a black hole right here, causing this area of space to warp more than this area of space, right? So the notion of distance in this area of space might be actually different than the notion of distance in this area of space. And so we're going to want to discover connections between these two. What are some interesting connections between these two guys, right? What's the notion of curvature coming from these two guys? But once we understand that, once we understand all that, then we can go and develop all of these guys that live in here too. So there's a myriad of things that live at one location in space for every point here, right? And another idea that's going to be essential to being able to do calculus on this space is if we were to look at a point, again, that's sufficiently locally can be sufficiently described in terms of being flat, right? So if I have some manifold, if we look at this really, really closely right here, at this point, we can essentially regard that area as flat. And then we can be able to do calculus. But again, that's later to come. All of this is later to come. And this is generally a broad overview. We're going to be interested in looking at what the various forms of the sky are. This takes on a list of forms: a Schwarzschild form, the Kerr form, the Ernst form, and there's a lot of other forms that this thing can take on, and it must satisfy the Einstein field equations. So it's not like there's an infinite number of forms that this thing can take. This has to be constructed in such a way to make this all true. All right. So we can't just arbitrarily pick anything for this to be. We could, but if we're interested in physics, we want it to satisfy this equation, right? And that's probably how far I'll go into this video. If you like this channel, go ahead and subscribe, and head on to my Patreon page if you're interested in this kind of stuff. I'll see you in the next video.